Welcome to the PS3 Test Review Learning Set 2. So this is for our the third physics textbook in our series. We do books 2 and we do books 3 at the 8th grade. And this is the second test of the book, covering lessons 4 and 5. So welcome to this review. Now the first question we're going to take a look at. The box in the picture is not moving. So when we look, let me grab a pen here. So when we look at this box right here, we know it's not moving. So I'm going to ask you a question. It might not be a box. It might be a can. Maybe it's a rock in the ground. Maybe it might be something else. But will give you the general gist of what we're going to be asking on a test. So the box in the picture is not moving. Explain why it's not moving. So the answer I commonly get for a question like this is, well, there's no forces acting on it. But now that we've been in class, we know that's not true. We know that the table is pushing up on it. And we also know that gravity is pulling down, and we've been calling that the weight because weight is dependent on gravity. So we know that's why there's no vertical movement. So the first thing you would have to talk about is that these two forces, and you can even say that the force of the table pushing up is equal to the force of the weight pulling it down, or gravity pulling it down. And because these two are equal, they're balanced. And because they're balanced, there's no vertical motion. So the more that you can tell us, the better off you'll get for a grade. But that's not it. So that explains why there's no vertical or up or down motion. So it's not going up and it's not going down. But the second thing you're going to have to talk about is, why are there no horizontal motions? Why is it not moving to the left or to the right? Any ideas? Now, if you said that because there are no horizontal motions, you're correct. So there's two things you're going to have to say. One, that the vertical motions are equal, they're balanced, or they're in a state of equilibrium, so there is no up or down motion. And you can even talk about how the table's pushing up with the same amount of force that the weight's pulling it down, so they're balanced. There's no vertical motion. And there's no horizontal motion because there are no forces acting on it, horizontally anyway. So those are the two things you'd have to talk about to get full credit for this question. Now here's a different question. Explain the difference between static friction and dynamic friction. Now the word dynamic, you may see this, or your instructor may refer to this sometimes as sliding friction, because it happens in our experiment when we slid the books across the table. That was dynamic friction. So sometimes they'll call it sliding friction because they slid across the table. Or the other term I'll commonly hear is called kinetic friction, because there's movement involved. So if you've already figured out, dynamic friction involves movement. Okay, so things that are moving. Static friction is the opposite. Static friction, there is no motion. Now, this is tricky. So a lot of times when we think of this, we think of, a brick sitting on the ground and it's not moving. Okay, you're right, that's static friction. Or if we were to have a ramp and that same brick is on the ramp and it's not sliding down. Okay, that's static friction. But think about this. Okay, you've got a car tire and you have that car tire on the road. Now, as this car tire moves on the road, would that be static friction or could that be dynamic friction? Because it takes the wheels going against the road to get it going. If you had a car and you were running the engine, but yet you had the wheels, or you had the whole car up on blocks or something, or a lift, and it wasn't touching the ground at all, the wheels would just spin. So the wheels have to come in contact with the ground in order for movement to take place. So if this car tire is rotating on the road, when it catches the road, it's not sliding or slipping on the road. That would still be considered static friction. Now, if you were out on the ice and every time you pushed on the gas, the wheels just kept spinning, Okay, that would be dynamic friction. But if you have good traction and these tires meet the road and they stick to the road and that's what causes it to go forward, technically that's still static friction because it's not sliding on the road. So make sure when you talk about the difference, the main difference is static friction does not involve motion and dynamic friction does involve motion. Another question. Is the strength of the friction force between two objects constant? Explain. Now this is something we've talked about in class. And if remember, we dealt with it in one of the readings. And remember when we talked about the bed. And on the bed, there was someone pushing the bed. And it was a young girl, I believe, in the story. And when she pushed a little bit, the bed didn't move. And when she pushed a little bit, there was a little bit of friction. But later on, she tried pushing even harder. And when she pushed even harder, she still couldn't move the bed because the amount of friction increased. Eventually, she had to get her brother. And when she and her brother pushed, the bed finally started to move. So, was the amount of friction constant? Did it stay at one level? And the answer is no. So when she pushed a little bit, there's a little friction. When she pushed even more, there was more friction. When she had to push with her brother, there was a larger amount of friction. It was even more. Now, eventually, friction can only go so high. There's a maximum level of friction. It only sticks so much until you overcome it. So it's not like there's always going to be the same amount of friction with the same amount of force that you apply. Otherwise, nothing would ever move. So to answer this question, is force, the friction force between two objects, constant? And the answer is no. Why? You can relate this story to it, but basically, as you increase the force applied to an object, the amount of friction also increases. And you can say, for example, in our reading, when the girl was pushing on the bed a little bit, there's a little friction. When she was pushing on the bed a lot, there's a lot more friction. Here we have another scenario. So we have Evan, and Evan kicks a football that's lying motionless on the ground. Draw a free body diagram showing the forces acting on the ball at the moment of the kick. Okay, we can erase that. So we got to do a free body diagram. So I'm just going to draw a block. And I'm just going to label this F ball for football. You can even put a hyphen there if you want. You can write it all out. So we got a football. So let's dissect this a little bit. So it shows the forces acting on the football at the moment of the kick. So there's still no motion. So we're going to have to draw an arrow here. And I'm going to say this is the foot because Evan kicked it. Now, at the moment of kick, I'm assuming the football is lying on the ground. Maybe it's on a football tee, but you're going to have some friction, aren't you? So I'm going to call that static friction because it was motionless. So we have static friction. Now, am I done? No. We can't forget about, okay, so if it's on the ground, it does say it's lying motionless on the ground. I'm going to have an arrow going up, and I'm going to label it ground. And what I want to do with these arrows is make sure that whoever's grading this, and remember, someone's grading your test, I always talk about you want to sell your answer. You want whoever knows that you're correcting the test, that you know exactly what you're talking about. So there's one more. I'm going to have a dashed line, and this is going to be the weight. So when you do this on a test, I've seen some people do stuff like this, where they just have arrows. And this is all they do. And what I would say is no, there's not enough information. How do I know how do I know that you know that this is the foot and that this is friction and this is the ground and this is the weight? You might be just drawing arrows because you don't really know how to draw it. So make sure you label everything. Make sure all the arrows are pointed in the right direction. Make sure, because this acts at a distance, it's a dashed line. So another possible question that you might see on the test. Here it says a vertical spring is compressed and a marble is placed on it and then released. The marble shoots up into the air. Use this information to answer questions 10 and 11. So there's no numbers on this one, so you don't really need to know that right now. So we know it's on a vertical spring, so it's going up and down. So I'm going to underline that because I know it's a vertical spring. It was compressed and a marble is placed on it and then released. So, okay, I just wanted to make sure I knew all the information that was in here. So the marble shoots upward because. So this looks like a multiple choice question. So the one thing I always want to do, I want to make sure I go through all 4 choices. I don't want to just get the A and say, ooh, I think that's the answer, but not look at B, C, and D. So, letter A. The elastic force of the spring on the marble is greater than the weight of the marble. So the elastic force, they say, is greater than the weight of the marble. Now this makes sense because it did say that a marble was placed on it and then released and the marble shoots up into the air. So if there was more force here because it's greater than the weight, that does seem to suggest that it would shoot up into the air. So I think this is the answer, but let me look. The elastic energy of the spring is greater than the gravitational energy of the spring. What doesn't this one mention at all? This one doesn't mention a marble at all. So I'm going to cross this one off. The marble's kinetic energy is 0. Wait a minute. The marble shoots up into the air. So is the marble moving? Yes. So this is not a good choice. How about this one? The elastic force overcomes the marble's gravitational energy. Well, the elastic force overcomes, well, it's not necessarily the elastic force. I don't think there's enough information. They need to say the elastic force of the spring on the marble is greater. The word, they don't mention the marble at all until here, but the elastic force overcomes the marble's gravitational energy. Well, the elastic force is great enough to send a marble up into the air, but yet it's not necessarily giving me all the details that I want. It's not necessarily that it overcame it. It's just that it was greater. So I really like this answer right here, and I'm going to go with this answer, A. So here's another question, and it's the second part of it. So if you remember the last one, we talked about questions 10, 11. I didn't number any of these, but here's the second question that goes with it. So again, this is the same information up here, but this is different. The marble goes up until it reaches its highest point. Okay, so it did go up and it reached its highest point, and then it falls down at the highest point. So now we're looking when the marble goes up and it comes back down, we're looking at the very highest point right here. So let me read them, and again, I'm going to read all of them just to make sure. A, the marble's kinetic energy is 0. Wow, kinetic energy is what we covered in our last unit. That seems to work because if it reaches its highest point, if you remember, when something reaches its highest point, it stops for a split second and then it starts to fall again. But I'm going to read the other ones. The elastic force overcomes the marble's gravitational energy. We had that choice before. But at its highest point, the elastic force is not overcoming the marble's gravitational energy anymore. Now, if it was still rising, that would make sense, but it doesn't make sense when it's at its highest point. The elastic force of the spring on the marble is equal to the weight of the marble. No, 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 no. What did I find? The elastic force of the spring on the marble is equal? It's not equal, because if it was equal, it wouldn't rise, it wouldn't go down, it would stay the same. So I know that's not the answer. So D, the elastic energy of the spring is greater than, this should probably be then, is greater than gravitational, or the gravitational, I guess it does work, is greater, no, there should be then the gravitational energy of the marble. The elastic energy of the spring is, no, this is what the answer was the last time. And that would make sense if we talked about it being maybe here. But if we're talking about the highest point, I guess this is the answer. Now, do you notice how I go through all the choices just to make sure that this is correct? So here's another one. Amelia hits a puck across the gym floor. She then observes the speed of the puck. Which of the following observations is most likely? So again, I'm going to go through, I'm going to look at these answers. A, the speed is constant because the force from Amelia's hit is still acting on the puck. So again, she hits a puck across the gym floor. She then observes the speed. So the speed is constant. I'm not sure. Let me go read the next one. The speed is decreasing because there is friction between the puck and the floor. So here it's constant, here it's decreasing. Here it says the speed is constant because there is no force acting on the side of the puck. Well, if the puck was hit out like this, if there's no force acting on the side of the puck, yeah, it's not going like this, but it would go straight. So we know this definitely is an answer, because how many times have you seen a puck curve like this without anybody else hitting it? And then this one, the speed is 0 because there is no force. Wait. The speed is 0? So you tell me if you hit a puck, there is no speed? If there's no speed, it shouldn't be moving at all. But here it says she hits a puck across the gym floor. So we know this is not the answer. So it's between the first two. So what do you think? If she hits a puck across the gym floor, is the speed constant? In other words, is it just going to go the whole way, never slow down, never speed up? Or is the speed decreasing? So when you hit it, it's going, but it's gradually getting slower. If you go, it's B, absolutely, it's B. So again, you see how I went through all 4 choices to help me figure out for sure what's the real answer? So many students sit and they pick the first one, or they see one that looks like it's true, and then, well, it's not. So make sure you read them all. So here's the last question in a review. On a visit to a science lab, Madison observes a piece of shiny material that is floating in the air. Okay, it's floating in the air. The material is not moving, okay? So it's floating in the air. It's not moving, so it's not going up, it's not going down. It's just floating in the air. What can she conclude about the forces acting on the shiny material? Oh, let me read these choices. Now you got 4 choices again, and I want to read them all. So the first one, gravity cannot be acting on a shiny material because it's not falling. Wait a minute. This is in... Well, if this is anywhere on Earth, and I guess it doesn't say it's on Earth, but I would assume it's on Earth, gravity cannot be acting on a shiny object. Gravity always acts on everything. Even when I go up and try and dunk it, it acts on it. So I know this can't be the answer. Gravity must be acting on a shining material, or it would be floating. Wait a minute. Gravity must be acting on the shiny material, or it would be floating. It is floating. It says it's floating. So this one actually makes no sense at all. There are no forces acting on a shiny material because it's not moving. Wait a minute. Didn't we just say that gravity always acts on an object? So I know this can't be it. Each force acting on the shiny material has one to cancel out. Yes, this makes sense. So we don't know what that shiny material is. This may be a type of metal that seems to be floating in air, and maybe below it, towards the bottom, you have a giant magnet. And just like in one experiment where we had the magnets and or the test tube, and we had one magnet inside and the other magnet seemed to be floating. So maybe that's what you have here. Gravity would still be pulling down, but maybe the magnetism, I guess that should be dashed still, is pushing up on it. So that might be the shiny material. Maybe it's a liquid metal. We do have some liquid metals like mercury. So maybe it's a liquid metal that's actually floating because of something similar to that. But again, did you notice how I read all 4 choices and I decided which ones definitely aren't it? And that really helps me figure out what's the correct answer. Now, this has been the review. So as always, if you have any questions about anything on a review, please feel free to ask your science teacher. Thank you, and good luck on your test.